Okay, let's restart. So please, could you, yeah. Oh, no. Mine first, okay? Nope. Yes, thank you. Okay, well, for those who are arriving now, I am Marcelo Pavanello from FEI University, and we are then finally starting the mini colloquium, the 2023 EDS Brazil mini colloquium. It is a part of the Shipping in Rio conference, and I'm very glad to be here with you, and that we are able to start. So our program is this one, and then we are moving to high-performance quantum computing in nanoelectronics, given by our colleague, Dr. Adam Skorek. But before saying this, I will leave this part to Adam, because Adam told me he would speak on that. And I would then first, as we are formally starting the mini colloquium right now, I would like to first thank the program chairs, Professor Michele de Souza, she was there in a while, and Professor Valeria Kiushitska also, who let me organize the mini colloquium. I also would like to thank Professor Patricia Lustosa, she's right over there, and the conference chair. She made a huge effort to put this conference on, and we are pretty much aware that it's not easy to do that, and especially because since several years, this is the first time we are meeting each other face to face. Then the challenge of putting that stand is not easy. Well, there are here some information about the sponsors of this mini colloquium. This is partially sponsored by Electron Devices Society. So Electron Devices Society has a program named Distinguished Lecturer Program, in which any of us, any of the chapters over the world can invite the distinguished lecturers to give special talks, and the 3 talks we will have along this day are from distinguished lecturers from EDS. So they are partially sponsoring this mini colloquium, as well as the other sponsors who made the Shipping Rio a reality, right? So with no further delay, let me just also finally comment that the FACE Electron Devices student branch helped to the organization of this mini colloquium. I am their advisor, but most of the work they made, so I would like to thank them also for their huge work in organizing mini colloquiums. This is not the first one, but every year we organize one, and this year the student branch also helped us to organize this one. Well, with no further delay, let me just move on to the Professor Adam Skorek presentation. But before going directly to the presentation, I would like to say a few words about the long list of contributions for Professor Adam Skorek, who honored us with his presence today. So I tried to compress, I must say. I tried to compress the list of contributions, but it is quite important for me to read all of this. Professor Adam is Life Fellow for the IEEE, and he completed the Bachelor and Master of Electrical Engineering program at Biacost. Oh, I'm sorry. Yeah, exactly. Precisely. University of Technology in Poland, received both Master and Engineer degrees in 1980, participant of the Electrical Engineering Faculty Doctoral Studies. He received a Doctor of Technical Science degrees in Electrical Engineering at Warsaw University of Technology in Poland in 1983. From 1983 to 1987, he was a visiting lecturer at the Institute of Telecommunications in Oran, Algeria. In 1987, he joined the University of Québec at Trois-Rivières. Is it right? Okay, perfect. Almost there. Where currently he's a full professor and director of electrothermal management laboratory. He founded the UKTR, which means the acronym over here, Electrothermal Management Laboratory, which succeeded both the National Nanoheat, Laboratory and, I missed it, UQTR, Industrial Electroheat Laboratory, founded and directed by himself since 1989. He's conducting electrical engineering courses for bachelor, master, and PhD students. His research works were granted by NCERC, CFI, and so on, as you see here. But this is not the last one. Okay, you can find some additional contributions here. Yeah, but I will do it. Well, you can see he published or co-authored over 150 papers, including works on high-performance computing applications in electrothermal analysis and so on. There are several publications available in IEEE Explore, and I will let you with some time to read the list of contributions. Do not bore you listening my voice, but I would like to remark this ended part here. He is Distinguished Lecturer from Electron Devices Society. He is recipient of the IEEE Industry Applications Society Distinguished Service Award, recipient of the Queen Elizabeth II Diamond Jubilee Medal in 2012. He received from the President of the Republic of Poland the Gold Cross of Merit and Knight's Cross of the Order of Merit of the Republic of Poland. We received from Poland in Chicago, Illinois, the Rooster Brotherhood Knight Order of St. John Cantus. Well, I do apologize, Adam, because my poor way of reading at this distance and my myopia cannot allow me to read very well. But this can give you an idea of the caliber of the people, of the professor that is speaking with us today. So I hope you enjoy. Adam, the stage is yours then.
Thank you, Marcello. So, ladies and gentlemen, that's what you saw here. It's simply I have an age. If you will be older and older, so you put all your stuff on the list, and this is what's happened. But what is fantastic to see students here, this chapter of the Electron Device Society from your university, which is absolutely fantastic and amazing. The students, you were the future, and today we will talk about the future. Professors as well, distinguished colleagues. That's Marcello. Thank you very much for this invitation. I see some of the fellows on this particular room, so thank you to be there. And Patricia, Michelle, just thanks for all organizations. Today I said, what I can tell you, I don't like to put you on my particular achievements or something like that, but I will try with you to go, like it's the tutorial, to learn something and to use it immediately, not tomorrow, but today. You can access what is technologically possible, and the big secret inside will be the freedom, and that will be free. So you can just use that, and we will see how we can do all of that. So I choose high performance quantum computing in nanoelectronics as a topic, and I just left traditional methods to present what we can do. Every slide have a link, but I don't have the computer here. Usually I'm doing myself all stuff, but we will try to work together, and we will see what will be possible to do. So let's start with the first, maybe like that. It's running this side or this side. I will try to move. Yeah, we'll move maybe on the first side. I went in Rio several years ago. I went to Corcovado, and I saw Marcello sending me the invitation, so I answered him, yes, I will go. And after 20 hours of, drive, flying here, I'm so happy to be there that, yes, I will return to Corcovado maybe Thursday, but today I'm with you, inviting you to do something and to discover what that we have nice. If you can just go through the click at the inside, we will go to that IEEE. So you see this Electron Device Society is the part of the IEEE that's supposed to change the screen. Once we'll work with another one, no. But what is this organization? The biggest technical society in the world? And that anyone can tell us, oh my God, some Americans should do their stuff. Or we have some publications. We have, if you'd like to be the professor, or if you'd like to have a nice PhD or postdoc score, so you will have all this stuff. You can remove this to go out like that. That's absolutely perfect. But I start with the first secret of the IEEE. IEEE, that's the people and the people. So why IEEE is so amazing that you will see several of them that will be with you here, several of them we will meet worldwide. And if we have a social media, that's very easy to go through the planet and to have so many friends. So for the students like you are here, and if you'd like to have the fantastic life and fantastic the people you will meet there, here in person, but let's say something 120, 30,000 students around the world, that's for you. And for all of us that we have several experiences already there, we can interact and we will see each other. Even with Marcello, we just wrote few words, so we become friends immediately. We saw each other face to face today, the first time ever. So for the IEEE, let's see, and usually I'm going through what is inside, but we work with matrix. Matrix is like a line and columns. So like the line in this matrix, we have 10 regions in the world. And like the columns, we have 37 societies. So let's put maybe on my presentation what's again, it's a little bit difficult to change, but we will arrive if that will be there. So in this 10 regions, 6 is US, and we have, let's go through that. Yeah. 7 is only one region in one country, that's Canada. So I can tell you for hours what's happened in the IEEE Canada, but let's see, that's region 7 up to the United States. And if we pass through this first region, we will go to the region that's 8 and 9. That's and for the 9, the region 9, we are here. That's the fantastic one, starting with Mexico. We discussed that we will put the bridge with Canada and Mexico, so we will have the direct contact together. And I said, yes, we have so many sections in the world, like 330, but let's see now, yeah, for this second one, this one maybe, yeah, for all societies. I invite you to go through all of that, and our profession, IEEE, it's absolutely everything, starting from power, going through computers, by biomedical applications, and if you'd like to put these organizations as yours, it's not necessary even, and that's maybe another secret, to use several resources there's not necessary to become a member. Please become, because for you, like you were on electrical and computer engineering studies, it's extremely important to be a member. You're starting in the early the possible, and you can have after that any advantage that can be for you year by year with the IEEE. There is something amazing. I don't like to sell the membership, but myself, I'm something like 36 years on this organization. I can tell you that's the best one and best thing I made in my life, even professionally speaking, for that. So if we move a little bit forward, that's from yesterday. 6 million items in IEEE Explorer. What's now and today publication means. Surely this at university in the professors milieu or this, even for the industry, the people will tell you, let's publish, publish, and publish. But the answer is simple. Yes, you can click on your Instagram, on Facebook, and you are publishing now. And if you ask yourself what you consulting every day, is the IEEE transaction or your social media, and just have this answer for professors, that it's extremely important that we must be inside of this particular movement. Why it is important? Because you know that now it's and discussion like that people with Nobel Prize laureate. I met several of them in the May of this year. And what's happening in the world? What's the question? How we can be an authority? Authority again. That's the real question. There is this authority again for everybody, for the populations. Is someone that's in the news tomorrow will tell about what's happened in this room? No, you will see that will be all other things, but the power, intellectual power that we have here, it's absolutely amazing. Why? Because we put this power through this stuff. It's important to have publication there. But today, that's the social media is absolutely the power bigger in any army in the world. And from this discussion, there's a Nobel Prize Summit in Washington. The conclusion is we must take seriously this the action, and for us this action is extremely important. It's not that Facebook is used for anybody or Instagram or let's say LinkedIn, that will be something fantastic with Twitter. We notice what's happened, but IEEE, we have it, social media as well. I will invite you to use it. So in this room, Electron Device Society, one of the 39 of them, just like the columns on the IEEE, this one is so particular that, yes, we have several Nobel Prizes there. And let's just discuss today, who will be the next Nobel Prize laureate in this particular auditorium? Let's think, are you doing something that will really be useful, or just will discover that the world will be better? That is our mission, and let's say from Electron Device Society, something like 5 the laureates we have there. I met in May the General Secretary of the Nobel Foundation, and I discussed with him this opportunity to put an award called IEEE Nobel Prize. We don't have for the engineering something so important. IEEE, we have a prize like the IEEE medal, but we'd like to put $1 million, half and half, with this foundation, and I discussed with this gentleman, who is the #1 for the Nobel Prize in the world, and he asked me after that, Adam, what is IEEE? I said, oh my God, I'm the first ever to tell him what is IEEE. Why? Because we have several of them, but after that we lose this way. And I can guarantee, if you'd like today, think about something very special, something that you have a passion to do that. Maybe we pass through those quantum computing in the minutes after. You can just obtain fantastic results, and the people arrive to you, telling you, hi, you will have the Nobel Prize. And this is why, in this particular society, we are contributing as well, supporting you. Your job is fantastic in the place, but we will try to support you in all programs, initiatives. If you'd like to send me after that any request for any project, any humanitarian project, you can do this, and you will see why and what is extremely important in my next few words. So the EDS is with us. Standards, IEEE, we are doing IEEE, and several numbers, we will change code. We will see that we are working as volunteers to put standards worldwide. And we are using computers. You never maybe realize that we are going to the IEEE standards for the wireless communications and for the power transition, transport, and etc. Yes, so we have all of them there. Television is as well something that you can see, and that's free. I'm not going through the links, but just inviting you. You go IEEE.tv, and you have all about what maybe it's today, no, but you will arriving home, so you can see what you missed on the presentation, just IEEE.tv, and you have your favorite channel. Next one is that I just particularly love that the people that I told you is doing IEEE. John Day. John Day, I met him one day in Argentina, Buenos Aires, and he said, Adam, 10 years, well, maybe 15 years ago, I founded IEEE TV, but now it's collaborating. Alors, what is collaborating? Collaborating, or corroborating, as you want, but you go through, that's the social media for it. IEEE, or if you don't like to pay this initial fee for students, it's so small as something $15, $20. Ask your professors, the professors will pay for you, what I'm doing usually. And let's try it. Collaborate, you will see. Let's see, there are several videos, presentations. That's the part, that's the social club, that you can be sure you are on the fantastic company there. And let's start now what I'm telling you that, about nanoelectronics and quantum computing. That's something that's, you know, emerging from what we do, from what we worked on it. There's your courses, there are classes, there's your projects, that's your future. And no, nanoelectronics is no more something that so we can be excited today, because the 1 nanometer, IBM tell you, yes, we have nanometer, we arrive on this level. 2 years, they tell us about 2 nanometers. What's happened and what the next step for is that will be the because the electronics, femto, atto, or something else. I met our colleague, fantastic guy, his name is Gordon Moore. You know, this Moore who telling us what's about the number of the transistor, what is prediction for the microprocessors, and is the Moore law now good enough? I don't think so. And if you will see, I prepared for to do something about quantum computers, and you will see. Today, the best computer in the world from June 2023, Frontier 1, okay, having the problem to compute for the same what is the best quantum computer doing. For quantum computer, you have 1 second. And for this, the best one in the world, the same problem, 47 years. Just imagine. 1 second, and we are talking something today. 1 second, 47 years. So if we learn about traditional way of the design, of the tests, of the production, so maybe it's not the good one. Maybe we needed to change approach. And people will tell you, hi, these guys from quantum, that have another kind of thinking. Oh, let's see what's happened for that. And as you can imagine, with the quantum computing, we have digital twins and AI. AI, that's that everybody's, even Dubai, you know, that they have the first ever minister of AI. So they said, that's so important, and they give the visa for the coders. But please, don't be just coders. Code will be generated automatically. But the human being must be the most powerful. I think that it's not processor or brain. Yes, the brain of all of that. And I will try to tell you some words about this high-performance computing, about what's that happen now in the intellectual properties. What about open access? And in this open access, I'd like to show you today, there's 2 or 3 places that you can go through, and you can use them immediately. And that will be some really modern. That's the case to open it this year. Or several of them already exist, and I will invite you to simply use them. And let's say something about what is this AI. If you'd like to go and if you'd ask an operator, but that will be too complicated. No, that will be too complicated. If I go, you can try to do that inside. You are going through the site, and you are putting this as a matter of the conference. Simply words, nanoelectronics, quantum computing, high-performance computing. Let's put them, and you will see in the moment, you will have all presentation what's happened there. So is this really necessary that the guy is arriving and we tell you this subject, because we can put and we have anything? Both are interesting. The first, the one, like here we have a tool, will tell us what is the knowledge of that. But what is inspiration? What is the way we can proceed? We discuss that today, here, in this place. And for this chat GPT, let's just put the question. Is the professors invited to that? On a regular classic class? Is like for the Google at the time. I remember the class, I think 20 years ago, I said to my students, hey, look in electrical circuits, we have Google. Hey, what you are doing, putting Google on the class? And you know what's happened now. And that's still the problem. We are arriving to our classes, we'd like to have our experience, and arrive to ChatGPT, and so, oh my God, it's what our place there. No, be happy. We survive so many things like that, like this one, we will survive and you will survive. If you see that maybe something is too classic for you in the class, so 2, 4, 5 years, what is for you absolutely modern and extraordinary will be the past. So that as we see in the other places like museum, this museum of the future that we are working today, and this one we will explain you what I'd like to just to bring there. And so for this ChatGPT, for all the social media that we can see, all our devices, this is the place you can check and see what happened there. Top 500. That's very simple. Top 500. And so if you'd like, I can leave this presentation PPT, so you just click and you will have the access for that. And there is the listing. There is the listing of high-performance computers for 2 times a year. This year, from June, I told you, that's the frontier. The from Cray is #1 with the AMD processors. And a few moments after, arrive that's to arrive to Google with that's the processor inside. And for this particular one, Google is telling, hey guys, we have something the better. We have now this quantum computer that is working as I told you. 1 second, 47 years. So this biggest computer in the world, yes, I work with the high performance computing for years. Yes, I paid something like $4 million for one computer, parallel computer, 64 nodes. It was in 90s. Now it's nice the decoration of my laboratory. $1 maybe for all of that. So we must push our money for all this stuff, and we must work every day on what we see, and after that, that will be switched to another things. Let's start immediately with it. And here on this the links, you see why it's so fantastic to work with the quantum computers. It's very easy. It's not something that we can, think strange. Is someone who is working now with this quantum computer here in this room? Thank you for this silence. After that, you will try maybe, and you will try. Please send me email, or just send me any to WhatsApp and everything you want, or the social media as well. You're very well invited. But let's try today. This is August 28, 2023. Thanks to Marcello, to Patricia, Michel. So the students branch, and let's construct, let's build the first quantum computer. Why not? Before you will build one, I will show you the place that you can use for free. That's the biggest place for this quantum computers here. I will show you that. I went it's something in July, the beginning of July, in Chicago. There was the quantum programming conference, and I have an access. So I simply discovered that it was already for a few months, but we will see. This one, as you can imagine, this picture is from my class. From my class 3 years ago. 3 years ago, a young man arrived with a piece of quantum computer and telling us, that's my qubit. So, what? And it passed like that. I went to see his PhD thesis defense. It was at Sherbrooke in Quebec, Canada. He moved immediately after that at Yale University and just be back to become a professor at the same university, surely in quantum computing. And so for the links, once again, if you need a presentation, maybe Jesse will assist me a little bit to tell us what is quantum computing. Can you activate this? That's 5 minutes. And Jesse, we will tell us a little bit what is inside. And after that, we will go through how you can use this kind of computers. Jesse, please.
Ideal quantum computer can break the encryption standards we use today by finding prime factors of a large integer in just minutes instead of the thousands of years it would take for a classical computer to do. But before you start to panic, while we have real quantum hardware today, it's not quite powerful enough to do that just yet. However, technologies are advancing faster than ever. The cell phones we have today are more powerful than the mainframes that we use to send people to the moon. And the researchers believe that we will soon entering an era of quantum advantage, where quantum computers will be used to accelerate classical computers, just like GPUs. In this video, I'm going to talk about 5 foundational topics in quantum computer: superposition, gates, measurement, interference, and entanglement. But before we dive into that, let's first talk about bits. Classical computers use bits, which are like switches. That can be a 0 or a 1. This way of computation has served us well, so well, in fact, that almost all modern computers work this way. However, this approach doesn't solve all the problems that we have today. Problems that can blow up exponentially and would take classical computers decades or more to solve. We already talk about the algorithm we use for encryption. Other types of difficult problems include optimization, chemistry simulation, and machine learning. Now let's talk about our first topic, superposition. Quantum computer does not use the simple 0 and 1 bits. Instead, it uses qubits. A qubit can be a 0, a 1, or any linear combination of the two. This spectrum of states is what we call a superposition. Our next topic is about gates. Similar to classical computers, we string together qubits using a construct called gates that can alter the states of qubits in the circuits. For example, we can have a qubit that's at the state of 0. Then we can use the Hadamard gate, or H gate for short, to put it in a superposition between 0 and 1. And of course, you can have multiple qubits with multiple gates in a circuit. For the circuit to be useful, at some point you need to read about its outputs, which brings us to our next topic, measurement. When a qubit is measured, it loses its superposition and collapses into just a simple 0 or 1. That means an arrow pointing this way does not measure a 0.5. Instead, it has 50% chance of measuring a 0 and 50% chance of measuring a 1. It is this in-between state that sometimes people say that a qubit can be a 0 and a 1 at the same time. It also means that just a small number of qubits can represent a large amount of information. So for our next topic, interference, we begin by addressing a common question. Why is that quantum computers can outperform classical ones? So if you remember, a quantum state is a linear combination of the 0 state and the 1 state. So an operation applied to this can be seen as applying to the 0 state and the 1 state, doing two calculations at once. It is this parallel computation that gives quantum its unique advantage. However, as you may recall, when a qubit is measured, it loses its superposition and collapses into 0 or 1. That means we can only get a single answer instead of all of the answers from this parallel computation. And to make sure the single answer we get is the correct one, quantum gates need to be arranged in a way so that it would amplify the correct answer and cancel out the incorrect ones, a process called interference. Now, this leads us to our last topic, entanglement. When qubits are entangled, their states become strongly correlated. That is, changing the state of just one qubit will change the state of another. For example, we can entangle two qubits so that their states have a 50% chance of measuring a 0, 0 and 50% chance of measuring a 1, 1, but never a 0, 1 or a 1, 0. In this case, if we change just the state of one, the other one would also change. So with the combined power of superposition, interference, and entanglement, quantum computer can solve things that classical computers simply cannot do today. It can lead to better drug discovery, or enhance the stock portfolio, or even artificial intelligence. Now we just need to wait for the quantum hardware to catch up. Thanks for watching. If you have any questions, please leave them in the comments below. Also, please remember to like this video and subscribe to our channel so we can continue to bring you content that matters to you.
But that's nice step after this theory will be how we can use it. And you know what's happened in our classical class. We put all theory, but after that we have an exam. And today there's no exam, but please, if you can move what is the video that I'm presenting there, and you will see what's happened as a link. If I will put, no, but can you just click and we will see what's happened here. Can you just, please, we just go through this IBM.com and you have quantum. In this link, you have an access, you will see. Please go down with this, that. Accept all, please. You can accept all to this. No. Go, down, one, and again down, and yeah, once again down. You will see this video after, not this one, no, go down. You will see something, yes, this one, thank you. And you have the access to the IBM the computers. The address is very simple, ibm.com/ or have quantum, and you can start with the free access to their computers. Look, this one on the left. Others, they will charge you something like, or charge us, but this one, the first, is free. If you'd like, and if you'd like to try today, quantum computers, what you can try as an algorithm, you can do that immediately. So I'm usually done that because the first time, some 2 weeks ago, I said to my PhD student, we have another problem, an algorithm for that. We try with Amazon, we'll try with the local quantum computers. But look, that's for free. And you have in your class today access to what we see and what they will present. To the nanoelectronics design, tests, fabrications. We arrive not only with what we told, artificial intelligence, but the digital twins of all factories. All factories, all foundries will donate on it. And today, we see on this particular site technical possibility to do that. Please move down, up. Can you go up and you will see video. Just play this video. It's not too big, 3 minutes something. Not this one. No, before. Yeah, and go. Yeah, this one. Yeah, please. You will see what about quantum computers for this kind and this place. We have free access, and let's try it. You know, the first experience with this quantum computer, I said, wow, that's the algorithm. It's really like with the classical one, but you have just this power. 1 second, 47 years. Let's see this video, please. Can you?
At any moment, there are as many as 10,000 airplanes in the air all over the world. Building and refining this global fleet has been part of the Boeing company's mission for more than a century. And our vision extends far into the future. The 787 Dreamliner continues our legacy of reinventing commercial aviation through unparalleled fuel efficiency and range. Part of what makes the 787 special is the extensive use of carbon fiber composites in its wings and airframe. This material is light and it's strong, allowing our airplane to fly farther using less fuel. That's opened hundreds of new point-to-point routes, directly connecting cities all over the world for the first time. Designing these composites is a tremendous engineering challenge. Robots apply layers of resin-infused composite material. The layers come together to create complex shapes designed for the rigor of air travel. The design of a single composite component might involve anywhere from 10,000 to 100,000 discrete decisions about how to arrange the material. And an airplane like the 787 has hundreds of composite components. Right now, no computer on Earth could handle all of those variables at once.
Classical supercomputers will never be powerful enough to tackle the full scale of Boeing's composite designs all at once. Classical computers rely on binary bits, 1 or 0. Quantum computers rely on qubits, which exploit the probabilistic laws of quantum mechanics to create larger, richer computational spaces. Right now, IBM has put quantum computing technology in the hands of more than 400,000 users all over the world. These researchers use our Qiskit runtime service to execute quantum programs at scale on our more than 20 quantum systems worldwide.
Our joint Boeing-IBM research team has demonstrated a new way of applying the special properties of qubits to create even larger computational spaces.
Our partnerships with clients like Boeing are helping us push the frontier of quantum research.
It's important for us as a business to be at the vanguard of emerging technologies. Our composite simulations are among the most complex quantum optimizations ever run. Today, we have a better understanding of how to transition from doing things classically to quantum classical methods of the future.
Thank you for this one. We will move after for what so we can imagine like our own production of this kind of computer. and said, yes, we have share opportunity to do that. I will move maybe to not to match the video on it. Can I go? Okay. I will try to change for another slide.
Today, I want to answer one question.
This one will be
how can I build a quantum computer? You may think about math,
superpositions,
superpositions, entanglement, and all these other buzzwords that you hear on the news. But what physically is a quantum computer? It's not any of these abstract concepts. It's something real. It's something physical that you can hold in a lab. Some of you might think this is an easy question. Oh, those cold metal chandeliers that we see in those IBM videos. Those are quantum computers, right? Well, kind of. Those are actually the cooling mechanisms that are used to keep quantum computers at near absolute zero temperatures. So the question still kind of stands. What are these things and how do we make them? Unlike classical computers, which have been optimized for the past 60 years using transistors, quantum computers still have a bunch of possible different implementations. We're essentially in the vacuum tube era of quantum computers. We can make a few qubits, and we can do some cool operations with them, but we haven't gotten to the point yet where we can scale up to billions and billions of qubits like we have with transistors. So a normal classical bit made out of a transistor can be in two states, either 0 or 1. In the 0 state, the transistor is off, and in the 1 state, the transistor is on. Quantum bits, or qubits for short, must also be able to have two states, a 0 and a 1 state. The difference is that quantum computers must also be able to be in a superposition of the 0 and 1 state. A superposition is just when you take one state and another state and combine them together by adding them. We can combine these states using constants out front that tell us about the probability that we will measure our quantum system in one of these given states. Now, most of the time, these states are energy states. The 0 corresponds to a certain amount of energy, and the 1 corresponds to a different amount of energy. By interacting with our system, i.e. shining a photon, or using some other method of putting energy into our system, we can drive transitions between the 0 and 1 states, or put our qubits into a superposition. So now that we know what we're looking for, we can start looking in the lab for quantum systems that have a 0 and a 1 state, two different energy states that we can go between and use as our computational basis. To do this, we solve the Schrödinger equation. The Schrödinger equation is a differential equation that allows us to solve for the energies allowed in a specific system. Because we're in quantum mechanics, not all energies are allowed. In fact, only a certain specific set of energies are allowed in a quantum mechanical system. All other energies are forbidden, and we will not measure our system ever to be in that energy state. For example, if we take an equal superposition of the 0 and the 1 state, that does not mean that our particle has half the energy between the 0 and the 1 state. What it actually means is that you have a 50% chance of measuring your particle in the 0 state and a 50% chance of measuring your particle in the 1 state. There's no classical analog to this. You can never have a switch that has a 50% probability of one thing or another. This inherent uncertainty is actually where the power of quantum computing comes from. If we go a little bit deeper, a quantum computer must satisfy several criteria. These criteria are known as the DiVincenzo criteria and describe what a fully functional quantum computer must have. Well, that's enough stalling, but let's actually answer this question, right? What does a quantum computer look like? First, I'm going to talk about neutral atom quantum computers. Neutral atom quantum computers use individual atoms trapped in an optical lattice in order to do quantum computation. And we can address each one of these atoms by shining lasers at them. And then we pick two states in the atoms to serve as our 0 state and our 1 state. These two states are the hyperfine states of the specific atom that we're using. Hyperfine states are specific energy states that come from the interaction between electron and nuclear spin. We use these states as the 0 and 1 states, and we can use lasers to go between them. So, for example, if you wanted to perform a NOT gate where you swap a 0 to a 1, what you would do is shoot a laser at the frequency that corresponds to the energy difference between 0 and 1. You can calculate this using some basic physics formulas, but if you know the difference in energy between the 0 and the 1 state, then you can calculate the frequency of light needed to make the transition from 0 to 1. Another type of quantum computer is a trapped ion quantum computer. In this case, our qubits are no longer atoms, but instead are ions, which are charged atoms. Similarly to neutral atom quantum computers, the computational states used in these qubits are the hyperfine states of the ions. Unlike neutral atoms, however, the trapping mechanism is very different. Because ions are charged, they can be trapped using oscillating electric and magnetic fields. When an oscillating electric or magnetic field is applied to a cavity that contains ions, the ions can become trapped in the oscillating field. Then, to address the ions individually, we shine lasers at them to change them between the 0 and the 1 state. Superconducting quantum computers are one of the types of quantum computers that most closely resemble a classical computer. These are chips made in a nanofabrication facility, much like the computer chips that you use in your laptop, phone, desktop, or whatever. That said, there are some important differences between a classical computer chip and a superconducting qubit chip. A superconductor is a material that allows electricity to pass through it with no electrical resistance. If you look at a normal conductor, as you decrease temperature, the resistance decreases slowly. In many materials, this is where it stops. As you decrease temperature, the resistance decreases slowly, but it never reaches 0. However, in some materials, known as superconductors, there is a phase transition. This phase transition leads to a state where the material will conduct electricity with absolutely 0 resistance. This allows for some very interesting circuits to be made. Superconductors arise due to quantum mechanical effects, and so they lend themselves to making quantum computers. We can make superconducting circuits that work as qubits and use them very similarly to the trapped ion or neutral atom quantum computers. We can assign energy states to different ways that current flows. Depending on the type of superconducting qubit you make, and yes, there are many types, each one of them has a different circuit pattern, different components, different materials, and whatnot. But depending on the type of superconducting circuit you make, you get different modes of current flow as your 0 and 1 states. These 0 and 1 states, much like the neutral atoms and the trapped ions, however, are still good for quantum computing, and we can use them as our basis states. By sending in electrical pulses, we can swap between the 0 and the 1 states, much like we could with the laser pulses in neutral atoms and trapped ions. Spin qubits are similar to superconducting qubits in that they're made on a chip. They're not like individual atoms in the sense that you have a material that you're actually sending electrical signals into. However, we are still looking at single electron physics. You can use these semiconductor structures to confine the electron to a single area in space. Then you can use magnetic fields to split the energy levels of this electron. This is known as Zeeman splitting. Specifically, what we're doing is splitting the electron spin states. Usually, there are 2 spin states for electrons, spin up and spin down. Spin up and spin down are usually degenerate, which means that they have the same energy. There's no preferred direction for the electron to spin. However, in the presence of magnetic field, the electron spin does have a preference, and so the energy levels shift, which again is known as Zeeman splitting. By then using an electrical pulse, we can go between these 2 states and use them as our computational basis states. We call this concept spin because it interacts in the same way that a macroscopic particle with some charge on it would interact with a magnetic field if it were spinning. Quantum computing goes super deep, and this video just scratches the surface. Each one of these different types of quantum computers that I gave a quick 5-minute introduction into is its own deep research field with its own deep concepts. That being said, if you guys want to learn more about each type of quantum computer, stay tuned, because I'm going to be coming out with a series of videos doing deeper dives into the individual physics for each architecture. I'm also going to go over some more interesting different qubit designs that I haven't talked about here, things like NV Diamond, for example. Thank you guys so much for watching. I've been Lucas, this has been Lucas's Lab, and I'll see you next time.
Thank you for that. And that it was, there's something that seems to be what is arriving, something theoretical like that. It's really working. It's really the future. Yes, let's see it in
This video is sponsored by Qiskit. More details later in the video.
What's that you saw?
From the first idea of a quantum computer in 1980 to today, there's been a huge growth in the quantum computing industry, especially in the last 10 years, with dozens of companies and startups spending hundreds of millions of dollars in a race to build the world's best quantum computers.
For most of us, it's quite hard to get our heads around the world of quantum computing, and a lot of information about it glosses over important details. This video aims to clear all this up, and if you watch the whole thing, you'll have a very good overview of the different kinds of quantum computing, how they work, and why so many people are investing in the quantum computing industry. This is the map of quantum computing.
Quantum computers solve problems in a different way to the computers we're familiar with, which, from now on, I'll be referring to as classical computers. Quantum computers have certain advantages over normal computers for certain problems, which comes from their ability to be in a huge number of states at the same time, whereas classical computers can only be in one state at a time. To understand this and to understand how quantum computers work, you need to understand three things: superposition, entanglement, and interference.
How it's working.
The building blocks of a classical computer are called bits, and the building blocks of a quantum computer are called quantum bits, or qubits for short. They work in fundamentally different ways. A classical bit is kind of like a switch that can either be a 0 or a 1, which you're probably already familiar with as binary or binary information. When we measure a bit, we just get back the state that it's currently in, but we'll see this isn't true of qubits. A qubit is more complicated. For a useful visualization, you can think of them as an arrow pointing in 3D space. If they point up, they're in the 0 state, and if they point down, they're in the 1 state, just like the classical bit. But they also have the option to be in a thing called a superposition state, which is when the arrow points in any other direction. This superposition state is a combination state of 0 and 1. Now, when you measure a qubit, the output it gives will still end up being either a 0 or a 1. But which one you get depends on a probability which is set by the direction of the arrow. If the arrow is pointing more upwards, you're more likely to get back a 0 than a 1. And if it's pointing downwards, you're more likely to get a 1 than a 0. And if it's exactly on the equator, you'll get either state with a 50% probability. So that's the effect of superposition explained. Now we'll move on to entanglement. In a classical computer, the bits are independent from each other. The state of one bit is not influenced by the state of any of the other bits. But in quantum computers, the qubits can be entangled with each other, which means they become part of one large quantum state together. For an example, let's look at two qubits which are each in different superposition states, but aren't entangled yet. You can see the probabilities next to them, and these probabilities are currently independent of each other. But when we entangle them, we have to throw away those independent probabilities and calculate a probability distribution of all the possible states we can get out, either 0, 0, 0, 1, 1, 0, or 1, 1. The important point here is because the qubits are entangled, if you change the direction of the arrow on one qubit, it changes the probability distribution for the whole system. So the qubits are no longer independent of each other. They are all part of the same large state. And this is true no matter how many qubits you have. You'll also note that for one qubit, you've got a probability distribution over 2 states. For 2 qubits, you've got a probability distribution over 4 states. For 3 qubits, you've got a distribution over 8 states. And this keeps on doubling each time you add another qubit. In general, a quantum computer of n qubits can be in a combination of 2 to the power of n states. So I'd say that this is the core difference between classical computers and quantum computers. Classical computers can be in any state you want, but can only be in one state at a time.
Through this cray, and they just show us. Can you put video maybe? That's very short, 1 minute. So what is with, and you will see what's happened. It's very, very fresh. Like an event, and you will see, and we will see together where we are today with quantum computers. If not, can you Okay.
Google's quantum computer, Sycamore, did something that's going to break your brain. Once again, it achieved quantum supremacy by performing a calculation within a few seconds that Frontier, the most powerful supercomputer in the world, would take 47 years to complete. This is something similar to what Google did in 2019 with 53 qubits. But this time, Sycamore performed the task with 70 qubits. Qubits are the quantum equivalents of classical bits that can represent 1 or 0, or both at the same time, potentially allowing for certain calculations to be performed at astonishing speeds. Quantum computers are still in their early stages of development, but the progress that Google has made with Sycamore is a major step forward for quantum computing. It shows that these machines are becoming more powerful and capable, and it suggests that they could soon be used to solve real-world problems. To get regular technological updates, follow the secrets of the universe.
Thank you for this one. And this
episode is brought to you by Brilliant.
The last maybe
since the dawn of computing,
probably
a single construct has served as the
doing kind of supercomputing applications for nanoelectronics. Are you working with Nanohub? Nanohub is something that you know or not? Yeah. So I can recall you there's something 23 years ago, I was with the people from this National Science Foundation. They said, okay, we will put together something new that is called Nanohub. And in this, can you, okay. So this one is for Amazon opportunity. And I have this picture from Nanohub approach. What's that? You can do even nanoelectronics to teach. You can use Nanohub for some modeling simulations, and you can even use Nanohub for quantum simulation as well. And approach is you run from here, the application in virtual machine, and after that. You put your information again on your computer. And on it, you have all the computers in the US territories. It is why if you'd like to put some, the US equipment to work for you, that's the Nanohub. It's not any place for Nanohub that we can use from any place outside of US, but many of them are there. Nanohub, you will see probably this here, if I have another slide. Yeah, that's Nanohub, but that's used around the world. And let's try. Let's go there. I have usually my account, if I'm connected here, going to the inside. And I prepare for you for today something, to simulate two qubits. You can go there and you can play. Please note that the account on Nanohub is free. And this is 23 years old facility worldwide accessible. So for the teaching, for the learning, for testing, or even one day I saw someone that master's students at U of T in Toronto, Canada, working on modeling this kind of graphene. There's applications for this, the device, DPV, something like that. And I presented this model from Nanohub, and I said, oh my God, it's done. Yes, several models are already done. And if you can't see that, so it's often situation you are working in your laboratory, and it's already accessible for free. So please, if we can put now high performance computing as well as Frontier 1, what we told about, and if we try to apply it for the Nanohub, imagine what can be done. Yeah, that's from Nanohub application we have. This one is about digital twins going through, and you can see opportunities for the nanoelectronics and quantum computers, high-performance quantum computers for this the particular applications, we don't like to take time to enter inside. That's very fascinating things. Cadence, which is a sponsor of this conference, they're doing the digital twins, and let's imagine all fundraise for, I don't know, maybe for TSMC, let's say, why not? That will be put on a digital twins mode, and so we can produce any nano or pico and femto the electronics component. So that's the last the moment I have for you to enter on the time, and so we see for a few seconds what we can conclude. Let's conclude with maybe with this one. You will see all the others, and I will arrive with you for Frontier 1. Please, we will see what is now general thinking in the world about number one as the computer, and what we saw here as alternative for them. Can you go to the oh, sorry, about it's, yeah, you need, no, yeah, the first one. Go to the first one, please. Number one, no, go down. And on the list you have the first one, yes. Click, you have a link on it, on the first one. You have a link. Right. You have a link? Yeah, click on it, yeah. And go to this, you have this URL. Go to the URL, click on the URL at right. No, this one, yeah. Yeah, in this URL once again. The second one, yeah, this one. Yeah. And go to read the press release. And you would have, yeah, to the press release. And please go with this, yeah. Thank you very much for this one. That's you see the competition. What they are telling us is they're the first, and we just saw that's just next door. We have something in the relation 1 second to 47 years. So thank you very much for your attention. I will go to the last slide. Just to tell you once again, thanks, and you see all this stuff we pass through. Oh, this one is in Portuguese. You can see the Amazon is selling now access for the quantum computers. We can pay something, and we have nice, fantastic access for quantum computing, tomorrow's computing today. Obrigado for all you pass time with me and with us today. Thanks again.
Thank you very much, Adam. Well, it is very inspiring. I think everybody's shocked because there is too much information, but I was wondering if any of you would like to ask some question to Adam, starting by Edmundo. So I will switch. Would you please answer from here, and I will get this? Yeah. Thank you.
Thank you, Adam, for that amazing presentation. I come from an institute which is doing astrophysics.
Mm-hmm.
So you know, in astrophysics, we are collecting billions of tons of information. So our institute is one of the 8 astrophysical sites that collaborated in discovering the black hole in the Milky Way. So there are 8 radio telescopes around the world. So we are synchronizing all those telescopes, pulling down all the information and processing that information. So we started in 3 years ago. After collecting information from 3 years ago, so finally we were able to build the image of the black hole.
Mm-hmm.
So in looking at your presentation, so having access to a supercomputing system where we can process all that information, that would be amazing.
Right.
Really.
Thank you.
So that's come to my question. So how much power is the system consuming? Because for having these qubits operated, you need to go down in temperature. So that means a lot of power consumption because you have to use those cryostats.
The cryostats, that's the only issue you have. And the question is just for environment, but it's not imagine the power with the classical computers, even with this cray. So that the powers that will be even the megawatts to go through. But for this one, let's say in kilowatts, I can't go with that exact number, but it's very, very low. And what is interesting for you, and let's put this, if you see that for the first time for the black holes, now, what an exciting issue there. So you can connect to IBM, even for academia. I've spoken in Chicago with the director of this laboratory. They can give you the access, so you don't worry about the power. We just think about your the black holes, just put all this, and that will be my pleasure to put you together with the IBM, and let's discover. And if we see this relation, 1 second to 47 years, so to imagine. But please don't recreate black hole here. Even between Canada or Mexico, you would like to create one. It's dangerous, but yes, for your data, it's amazing, and you can start that immediately. And that will be my pleasure to help you with this contact.
Thank you.
Thank you. Any other question? Olivier.
Thank you for an amazing presentation. I have anyway behind this several questions. The first question is about the precision, because we are working with the probability of presence in a state.
Yeah.
So, as mentioned by our colleague working in Milky Way,
yeah.
You have to decrease the temperature. So the problem is, what is the level of temperature which is acceptable to have a minimum of precision on your number of states? I imagine that if the temperature is not low enough, you decrease the number of states, which is possible. So how to control this? How to be sure that we minimize the errors? This is the first question. And the second question is about, you speak about nanotechnologies. You present something which is big. So it's not nanotechnology in this case. You cannot put in 1 billion systems in 1 square cubic millimeters. So, of course, if the power is much higher, so we have not to decrease the size. But what is the balance between the size, the possibility of development? Do you need big systems in a building of 1 kilometer long, like we had 55 years ago?
Yeah, I see. Yeah.
Or something like this. I have not in my mind all the ideas.
Yes.
Sorry for this question, maybe it's difficult.
Yeah, no, it's a fantastic one, and everybody's working on precision. And if we put temperature, let's say the superconductors, it's not only at minus 270, and if you have that, surely you are precise as well. But it's not as so long. Somewhere in South Korea, the people say, "Hi, we have superconductors on the ambient temperature." So to be ready, and we must be ready that the progress is also there in materials, and we can reduce this temperature. The progress is working for this approach. So now how is the bigger? How is big this in Canada? Let's put 10 meters by 10 meters by 10 meters, 10 meter cubes. That's the biggest computer that you can have. As you saw, installation for that is cryogenic one. That what is the big? But inside you have the regular micro processor. You have the wafer, you have a nice production, and let's say if we have 2 nanometers technology, or even that's going to 1 nanometers, yes, this approach it's working for quantum computers. But what is extremely important, as you tell us, 50 years ago, I remember that it was, you know, a big stuff for what we have now, now here. But what is arriving, that's the future. And we saw this Schrödinger equation. What is, it's not evident for everybody. Let's ask politicians what is their understanding of Schrödinger equation. So the answer will be absolutely, I think, other that so we can expect. No, we can expect what they will do. So for that, the right questions, yes. That's what we think about, and really, you know, over the passing yesterday, just before I met you here, I put some updates for my slides. Simply, what I presented is really from yesterday. So that's it's really right now. And yes, we probably to go through something like, let's say, this one will be quantum. Apple or quantum, the smartphone, and that will be the size of it. Next one might be the watch, and next one, I don't know. It's another question.
Yes, well, we have some young scientists, some not so young like me, and let's assume we have the qubit already solved. So if you would say to this audience, what is the most challenging part on the system level? Would you say, is it on the control? Is it on the temperature management? Where do you see the most challenging part to increase the capability of quantum computing? This is my first question. I would like to hear from you.
I think the answer is temperature.
Temperature?
Yeah, the answer is temperature, and with this temperature, we will go for superconductors. That's my opinion, because all the other things we can manage as well. But for that, if we have opportunity to have this resistance as small as 0 in other conditions, that's so will be, and we will remove if we don't need it. This low temperature, this dimension of as we saw on the presentation will be like the classical one. So the answer, from my point of view, is temperature.
Okay. My second one is with regards to the interaction between the quantum computer and the overall world and overall electronic systems and so on. I don't know if it is easy to have a number, but how much we lose in this interaction in terms of power and in terms of speed? Do you have any clue, an idea? Because our world is binary.
Mm-hmm.
in the quantum computer, it's not a binary. So we have to change the information to the binary word. How much we lost?
It was already done for high-performance computers. This old approach for the nano AB. So you prepare your data locally. You are working on it without interaction with your quantum computer. And you're sending your task to quantum environment, and that will be inside. So we can tell it that interaction for this distance is not as we'd like to define, that will be in seconds, minutes, or months or years. That will be just the transfer. If you have a transfer of your data, the byte works on the computer, locally speaking. That's next door you have your computer in a very short period, but the transfer will take time. So that's depends of what the big your data is. Like you will have enormous one. So we will be absolutely fantastically concerned putting something in direct interaction. And to reduce this time, I will answer like that, this digital twins approach with the sensors, they will keep data immediately, and that will be connected as shortly as possible to this computer. So we will connect the data. That will be days, weeks, even years if we have something that big. But after that, if we have that on the digital twins on, that will be instantly. That will be microseconds, seconds, or minutes max.
Okay. Is there anybody who would like to ask a question to Adam, to take the advantage of his presence here with us? I think people is willing to lunch. So with that, I would like once again to thank Adam with an applause round.
Thank you for your attention. Thank you so much.
So we have now lunchtime. It's 2 hours lunchtime. We are back on, no? 2 p.m., right? No, you said no, it's 2 hours? No, not the 2 hours, actually. yeah, it's a bit day and a half. Yeah, sorry. 2 p.m., we are back for the mini colloquium. Okay, enjoy your lunch. Thanks.